Chapter 20, Think and Explain. So 43, why don't you hear the sound of distant fireworks till after you see them? This is very similar to a previous problem, that the speed of light travel is much faster. And we're talking 300 million meters per second for the speed of light and 340 meters per second for the speed of light, speed of sound. And so the light comes at us. So we're talking almost 1 million times faster, and so that's why we see it before we hear it. 47, why do flying bees buzz? Basically, their wings are flapping up and down. So it is pushing the air, creating compression and rarefaction in the air. And so as it's vibrating up and down, it does it at a frequency in which we can usually hear it. 51, sound from source A is twice the frequency of sound from sound B. Compare the wavelengths of the sound from the two sources. So the big question is, are they going through the same medium? Do they have this, and therefore the same speed? Let's assume that they do have the same speed. Therefore, if the speed is the same and that's equal to frequency times wavelength, then as the frequency goes up, the wavelength goes down, and vice versa. So one has twice the frequency, it should have half the wavelength. Again, assuming that they're going through the same medium. 55. When a sound wave moves past a point in air, are there changes in the density of air at this point? Yes, because you get air molecules sort of floating around like this, and as a compression wave comes through, you get them much more tightly packed, and that's usually followed by rarefied, so they're farther apart. And so you get these pockets of higher density, pockets of lower density. And the higher density ones is compression, the lower density ones is rarefaction. 60. If the speed of sound were dependent on its frequency, would you enjoy a concert sitting in the second balcony? Well, no. So the farther you are away, that means that there's going to be a greater lag. The higher frequency items would, if it says speed is dependent on frequency, let's assume it's a direct relationship, so the higher frequency, the higher the speed. So the higher frequency items, the like tenor sax, flutes, things like that, those frequencies would get to you faster than the bass sound. So the music would not get to you at the same time. Now, I would say that if the speed of sound did depend upon frequency, that the music that we have would be a little bit different, and you might still enjoy it because they would account for that. However, it doesn't. All right. Why does sound travel slower in cold air than in warm air? So in cold air, cold versus warm cold air means that the molecules aren't moving as fast. And so the sound still depends upon one object hitting another object, but if these objects aren't moving fast to begin with, that means, well, the molecules are traveling slower. A shock. If it's not moving faster, it's moving slower. So it just takes longer for the particles to get there. You're not starting out with the same initial speed. So that's it for 62. 67, why is an echo weaker than the original sound? There's actually two explanations for this. So as the sound goes out, it spreads out. And so you have that aspect of it. So if I had some speaker right here, it sends a pulse, a compression wave out in all directions, and that compression wave spreads out more and more, so the energy gets spread over a larger surface. Similar to light. The farther you are from light, the weaker the light is, fortunately, because otherwise stars would blind us. And so the echo is weaker, so you get that dissipation. And the other thing, it's an echo, so it's bouncing off of something. And unless it's a perfectly smooth object, when the sound hits it, things will bounce off in different directions. Now, the more that bounces back in the direction from which it came, you will get a higher quality echo, but sometimes it has to bounce off several objects, but the reality is you aren't going to have a whole lot of very smooth objects, and there'll be, even at the microscopic level, there'll be some dents and so forth, and so sound will hit, and even if most of it comes back at you like in a shower, some of it will shoot off to the sides, which weakens it further. 79, how can a certain note sung by a singer cause crystal glass to shatter? Everything has a certain natural frequency that if I hit a glass, then it makes a certain sound. And so if I think about a slinky, I've probably potentially done this in demonstration in class. I have a slinky dangling here, and I'm hoping you've played with a slinky to imagine this. I can get the slinky oscillating back and forth. Now, if my hand starts moving along with that, I'm basically, if I move at the right frequency, the slinky will start moving farther and farther. Now, a slinky is not going to break apart suddenly. I hope not, at least. I haven't seen it. But a glass has a certain structural integrity, and so as the molecules start vibrating more and more, if I hit that right frequency and so get them to bounce and I just add to it, then the glass eventually gets to the point where it cannot maintain the structural integrity, and that breaks or shatters. 84 piano tuner uses a 264 hertz tuning fork. Here's 4 beats per second. What are 2 possible frequencies for the vibration of the piano wire? So 4 beats is just the difference between the 2 frequencies. And so if 264 hertz is one of them, the other one is either 260, which is 4 below, or 268, which is 4 above. Either way, you'd get 4 beats. There really is no way to differentiate between those two unless you can actually hear the difference between 268 and 260. I don't know that I can, maybe. But that's it for the Think and Explain from Chapter 20.